Hey everybody, just gonna make a really quick video, just kind of walking you through these two labs here. Um, these two simulations. Circuits are when you don't actually have them in front of you to play with. It's a bit abstract. When we're in school, we would actually use real batteries. We'd use wires with little alligators clips, and I have resistors. And the first lab we'd do would be to get a light bulb to light with some batteries and wires, and that's always a really fun one. But you know, it is what it is, and we're just gonna basically work through some simulations this week and have fun with those. The one packet I've posted over on in the topic on the right there is the circuit simulation lab. This is pretty heavy duty, so you're gonna have few days to work through it. I imagine you're going to have some questions. Um, I'm gonna walk through a bit of that worksheet in this video here. Um, so this is the first lab you do, the Ohms Law lab, right? All you're doing is you're just changing the voltage and making note. As the voltage gets bigger, as you add more batteries, know how it adds more batteries. I love how it does that. You get more current flow. Now, this one's kind of lame. It's just some arrows and this. Resistance, notice those little black dots. It's trying to illustrate resistance. So you can increase resistance, but then you'll notice the voltage has less effect on the current. Anyway, you're going to make some observations with that. Now, the next lab, this is the big one, all right? Circuit simulation lab. All right, so really dial into this one here. You're going to go, I'm on the FET website. I am looking at the Circuit Construction Kit DC. Now, these are like the same thing, but Circuit Construction Kit DC. All right, I'm going to play that. Let me go get open the. I should have already had this open, but here's the PDF file for the lab. All right. I made the PDF file back in the day. Okay. And it has an older version of this simulation in the little pictures, but it's the same idea. Okay. Um, you're gonna work through this, and this one's important. So, take the week basically and work through this. Don't save it all for Thursday. Trust me. Don't get a start on it. Have fun with it. Um, there's some parts built into it where you're not actually going to you're not supposed to use the software here. You're supposed to use the equation you just learned. 4.7 K ohms. K means 1,000, so 4,700 ohms. 50 K would be 50,000 ohms. Anyways, you're going to work through these. I'll show you how to set up the software though right now, just to be able to kind of do that. Non-contact ammeter. Okay. Yep. Practice problems. Um, you change it to schematic mode. I'm not sure if this can do that or not, but we'll see. All right. I'm going to walk you through a little bit of it though. So the first thing we do is construct the following circuit. You need to check the box next to the ammeter to add the component which measures the current flow. Right click the battery and check show value. Okay. So we're going to go intro here. Maybe I should have done, let's see, maybe I shouldn't do the lab version. Let's see what that looks like. No, it's like the same thing anyways. Okay, so the ammeter, they don't have the one you can insert, I guess. Or do they? No. The dog. Oh man, classic. Try to get the dog to burn. All right, so the first thing you're going to do is set the circuit up. All right, so you grab the elements out of here, just drag and drop them. Let me go back and check what I have been making. Oh, I have a resistor in there. You can do that. I guess, I'm going to make a separate lab here, just a separate activity. You know what? I'm going to change this up. That Ohm's Law one is cool, but it's kind of lame. I'm going to change things up. I'm that Ohm's Law lab you can play with. I'll have you take a screenshot. But then this is what I really want you to do. I want you to get. I'm going to have you do this instead. Whoa, this is weird. This is different. So I'm grabbing the base and it's rotating it. First thing I want you to do is get the light bulb to light. All right. And you're going to take a screenshot. I'm being lazy with the wires right now. I should really make them look a little bit better. Uh, you know, but oh well. Bam! Light bulb is lit. Ammeter. This is the non-contact ammeter. This is the only option. Note, just like I said in the one video, the electrons are being drawn into the positive side of the battery. That's what current really is. So there's 0.9 coulombs per second, or amps, flowing through this wire. So that's the ammeter. Voltmeter, this is kind of a cool little device. What a voltmeter does is, if you put the red lead on one side and the black lead on the other side, it'll tell you the voltage across this battery. Now, I click show values, and look, 10 ohms is the bulb. That's the resistance of the light bulb. I can change that. Right, I can make it 100. Oh, right down here, I can drag it, I guess. Make it 120. The current slows down. It's not as bright. So it's pretty cool. You may hear your fan on your computer kick up when you are running this simulation, and that's what is going on. Now, here's the deal. I can take those wires and I can put them here. There's no voltage difference across this wire. So what you'll see is there's no voltage difference across anything unless you have resistance. All right, so that's an important fact. So notice when I put you should always, you should always start with your voltmeter leads across an object with the red on the higher side, the more positive side, and the black on the more negative side. And then as you move through your circuit, you move one to one side of the item, and then you follow it with the black. So you always put the red on the leading side. And what this will tell us is this is the voltage drop across the bulb. So the bulb is consuming basically the energy provided by the battery. It's kind of interesting. Here we go over here, electrons and conventional. So this is an unfortunate thing in history. Before we knew that electrons existed in the 1700s, Ben Franklin decided to call current flow the flow of positive charge, and that's what it would look like. All right, so when the concept of current flow was first invented, essentially by Ben Franklin, he considered it the flow of positive charge. It turns out that positive charge cannot actually move. Their positive charge is a property of protons, and they're stuck in the nuclei of the atoms that make up the wire. There's no positive charge moving. This is called conventional current. And in fact, this is how we actually always draw current, flowing out of the positive side of the battery through the bulb back into the negative side of the battery. What's really happening is electron flow, but we pretend that it's positive flow. You might say, why would we ever do that? Why wouldn't we just call electrons? Well, because historically that's what happened. And it turns out it doesn't really matter. In fact, every circuit you've ever owned has been designed by engineers thinking of conventional current flow. In fact, it wasn't until like my third year of microelectronic engineering at RIT that I fully understood that there was no such thing as positive charge. That in fact, after we designed crazy circuits with 100 components in it, right? And then we find out that really what's happening is there's electrons flowing out of the negative side, and it doesn't actually make any difference. If a negative charge moves from left to right, that's equivalent to a positive charge moving from right to left. So in fact, it basically just acts the same way. It doesn't matter. So you probably want to leave it conventional current flow for this activity. So this is gonna be your first thing. Basically, set up this circuit. Just don't take a screenshot of mine. Make sure the wires look a little different, and submit a screenshot. So that's what I'll have you do. And then to change the battery, I'm definitely gonna have you do this with this circuit. I'm gonna have you do this with the this lab and not the Ohm's Law one. Now, I can drag the voltmeter back there. All right. As I increase the voltage of the battery, the current goes up. So if you click on the element, you can drag this around. All right, I can really make things go crazy. You can mess around with, and this is what we would have done in class. You can try putting other things in here. Delete this wire, and I'm going to put a dollar bill in here. What the heck? Oops. What happened there? Did it attach? I'm not sure if it attached or not. I guess it did. No, it didn't. Not sure what's going on. Oh, the wire attached there. That's what happened. Oh, this new version's a little bit finicky. All right, that's okay though. Boom, boom. We've got no current flow. You used to be able to make the battery even bigger. It was like a way to increase the voltage to some absurd amount. Um, Basically, it's too resistive, so you take that out. You can put the paper clip in there. Bam, metal, so it conducts. And you can test these different things. People used to try to fry the dog, but I think they make the simulation so you can't fry the dog. But anyhow, that's the basic use of this. To set up that first circuit in the lab activity, what I would do is, I'd kill the light bulb. Let's get that. Let's go back up over here. Let's get that resistor out. All right. All right. Connect up some wires. I'm going to make it look a little bit better this time. It'll provide me with some more flexibility later on. There we go. The voltage, I'm going to drop it back down to 9 volts or so. I think you can type in here. Oh no, you used to be able to type in there. So it goes by half volt increments if you click the arrow. So that's good. Yeah, and then we're gonna increase the voltage, measure the current. So you got to get that ammeter and go. So that's the first page. Then there's some guidance on what happens with the current flow, what a current means, Ohm's law. This is the slope of the line that you plotted. And then series circuits. Okay, so I'm over on page 3. When you want to start the series circuits, break one of these junctions, widen it up a bit. All right, and we're going to add, you don't need to add the switch in there. I have a switch in there. You don't have to do that. When you want to do the series circuit, we go like this. So now what's the current flow? Oh, it's only 0.45 amps. Now that's interesting. Okay, cool. Over on page 4, some questions. How does it compare? Using the supplied voltage and supplied current, calculate the total resistance of this current. So using Ohm's law, V equals IR. What you're going to do is say, okay, R, the total resistance of the circuit is V over I, so it's 9 over 0.45. That ends up being 20. 20 ohms is the total resistance. So look, when you have a series circuit, it's called series, the total resistance of the circuit, you just add the two components together. You're going to add that. I think I have you measure the voltage across each component. Did I have you do that using this? Third resistor, using potential. Okay. Okay, so the current doesn't change from location to location, but what's kind of interesting, I guess I didn't ask you that question. I should have. If you take the voltmeter, it's kind of cool. Is 9 volts are the battery. If you look at each resistor, each of them drops 0.45 volts. The total together, they drop 9 volts. So that 9 volts of the battery, I think of this as like a chairlift or a ski resort. The battery is like the chairlift. It gives you the energy. Then the resistors are like the downhill portions. And then everything after the resistor, the wire, is just like the flat portion where you're trying to get back to the chairlift. Hopefully you have just a little bit of kinetic energy left so you can slide all the way back to the chairlift, get a boost up. You drop some of your energy through the first resistor, the first hill, then you go down the second hill, you drop the rest of it back to the bottom, and you're there. So as you have a loop through the circuit, your total voltage adds up to 9 volts. All right, pretty cool. Some practice problems over on page 5, and then we go into parallel circuit. Parallel circuit's a little bit different. I have you change it to schematic mode, which shows you, this is how we, so let me turn off the current for a second. This is how we draw them. You don't have to change your schematic mode. You can leave it like that. So schematics are how we draw circuits. All right, so I gotta break some of this up. Parallel now is going to be kind of wacky. Got to get the stuff out of the way. All right, they're going to be side by side. All right, get a resistor in here. I want to just get that side up. All right, cool. And then this, I'm going to delete that. I'm going to bring this here. I need one more wire here. I don't know if it'll allow me to, it's not going to allow me to just go in there randomly. Okay. That's kind of annoying, but oh well. One more over here, one more thing. Bam, bam, bam. Boom. I'll show the current. All right, so this is kind of cool. In parallel, they're next to each other. You'll see 1.8 amps of current flows in, but then when it hits this junction, look what happens. 0.9 and 0.9, it splits up. 0.9, 0.9, they meet back together, and there you go, back to 1.8. So this is like the chairlift, but then the trail splits. See, in series, there's only one way down. In parallel, there's two ways down. But the two ways down, no matter what, you still have to go down the same amount. So when you start measuring voltages with this one, what you'll see is each resistor has a voltage of 9 volts, or dropping 9 volts, I should say. So each resistor drops 9 volts. Because, you know, if you're a charge coming in here, if you're a current flow, you get to this junction, you have to split. You got 9 volts of energy, basically. You got to get rid of 9 volts of energy through either path. So you get rid of your 9 volts of energy, you lose it. How is this energy lost? That's a good question. It's heat. Resistors generate heat. So the energy of the electrons gets converted into heat. Light bulbs, it gets converted into heat and light. So it's kind of interesting. But yeah, so that's basically how you do this. You can answer the questions, work your way through it. On the last page there, something I want to show you, the kids always mess up on this. On the page 8, you can see what the software used to look like in page 8 here. They used to have like a real picture of a multimeter, which was kind of cool. You're not gonna actually build that circuit. You're gonna stick with the circuit you had back here in the parallel circuit. You're not going to build this circuit. Don't ignore that. I don't know why I haven't ever updated that picture, but I haven't. You're going to measure voltages across all the parallel resistors, and then you're going to make a new series circuit, draw a schematic, measure the voltage across each resistor and the current flow, and then answer these questions. All right, and then there's a summary page of circuits. So do your best with this week. I'm going to change up one of the assignments a little bit, which you probably won't even notice because by the time you see this, it will have already been changed, and we'll be good to go. All right. We'll see you later. Have a good one. Stop.